Good morning students. In today's class we are going to take one more step into circular motion, that is uniform circular motion. We see a relation between this rotatory motion or circular motion and the linear motion, that is which is going to take place along a straight line. How we are going to relate these two quantities, that we are going to see as a first step. Okay. We see the relation between velocity, linear velocity, and we call this one as omega. It is called as angular velocity. In today's class, we see this relation. In the case of this circular motion or rotatory motion, the object or the point is moving around a fixed point. Then, if it is moving like this, then it is going to have the distance along the circumference of this one. That is, if it starts from point P, then after time, if it is at P1, then at the center it is making an angle some theta, let us say. Okay. Then if it takes t time, then the angle made in t time or with respect to time, we call this one as angular velocity. Angles are dependent with time. Okay, the rate of angular displacement. This is called as angular displacement. The rate of angular displacement is called as angular velocity. It is denoted with a letter omega, a Greek word omega. This is a Greek word. Okay, not W. Okay, we see the relation between this linear velocity and angular velocity in our class. And also we have to remember that if it goes on continuously in this type of motion, then after a certain period of time, again it is going to back at the same position. That's why in general this angular velocity is also called as it is moving around a point continuously repeated, we call that one as frequency, angular frequency or angular velocity. Okay, we see the relations between them now. Okay, for this one, we just take this uniform circular motion. We take the center as C, the initial position as P. Then, after time delta T, the particle is present at P dash, P1, P1. We just take this one as radius R, radius R. Okay. Then this is angle section, then this delta theta or delta theta. Then during this interval of time, the displacement is, we call this one as delta S. Delta S is the displacement. Okay. Now, we call this one as delta S. Now, we know the velocity. It is defined as linear velocity. Okay, delta S by delta T. Okay, the change of displacement with respect to change of time. And similarly, we define this angular velocity omega as delta theta divided by delta T. Now, we have to relate these two quantities. For that one, if you go to this triangle or this part of this circle or this center, then okay, if delta T if delta t or when delta t tends to 0, that is for a small change of time, okay, this comes close to this one, then in that case we can write the relation between this one and this one and this one. We can write delta s as r into delta theta. Delta s as r into delta theta. Now, that is, this is for small values of delta s and delta theta. We can write this equation. Okay. Then, if we substitute this value in this equation, therefore we can write v is equal to instead of delta s, we are writing r delta theta by delta theta. Then v is equal to r into omega. V is equal to r omega. This is the relation between this linear velocity and angular velocity. And up to now, we did not talk anything about the directions. Okay, if you simply take the magnitudes, v is equal to r omega. Okay, now I try to explain the relation between these quantities in a vectorial picture. That is, if we write the same thing, we write v bar is equal to omega bar cross r. Okay, and we know that this is cross product. Cross product is, we have to write mod omega mod r sin theta into n cap. Okay, when do we get this condition? If we are having a maximum angle, that is 90 degrees, then sin theta is equal to 1, we won't get any sin factor there, r into omega. That is, to understand this one, suppose if you take the uniform circular motion on a horizontal plane like this, okay, and if this is the center, and if you consider this point, the velocity is present along the normal direction. Tangential direction. This is the radius. This is vector. This is vector. Okay. Then, how to consider the direction for omega? Okay. It is taken as along the direction of the axis of this one. Okay, omega. How we are going to write the equation means, we are defining v bar is equal to omega bar cross r bar. Okay, then if we consider this type of plane, this is a plane in which the body is going around this point or axis. Okay, now we fix these directions by making use of a right hand rule, a right hand screw rule, or right hand rule. Okay, for this one, see, we are writing omega bar cross r bar. We have to fold our fingers right from omega direction to r direction. Then the thumb gives the direction of velocity. Okay, that is, if we hold our fingers like this, then this gives the direction of the velocity. It goes like this. Okay, like this it is going to have the motion. Okay, this is how we are going to fix the directions for these quantities, and this is the maximum value of the term, as there is no sign factor. Okay, and these types of vectors are called as axial vectors. Okay, they act along the axis. With respect to the axis only, we are able to understand the rotations. That is the meaning of that direction. Okay, by seeing from the top, we can understand the circular motion in that plane. Okay, that's why we are going to consider the directions like this. This is the relation between these vector quantities. If we simply write in magnitudes, v is equal to r omega. Okay, but you have to follow this order. This is for right hand. Okay, in this way we write the relation between velocity and angular velocity. Velocity is a linear quantity, angular velocity is a rotational quantity. Okay.